everyone, welcome back to the discussion on continuous functions. In the previous two videos, we have learned what continuity means and what are different types of discontinuities. In this video, we are going to practice some miscellaneous questions on continuity. So let's begin with the first question. Look at this function. The question is to test continuity for a function which is defined as a branched function. By a branched function, we mean functions which are defined in branches. They do not have the same definition all through the domain. You can see that the domain of this function is 0, 1. The domain of this function is 0, 1 and the definition of the function has been defined separately on different parts of 0, 1. 0, 1 has been fragmented into different segments and the function takes different values on those segments. Now for testing continuity of such functions, we always test continuity carefully at the breakpoints, because on the different subdomains we can see, this is a linear polynomial, so on 0 open half, this is very much continuous. Similarly on open half, open 3/4, it's very much continuous, being a quadratic polynomial. Similarly here also in this branch it's continuous, but wherever there is a change happening, the change is happening at 3/4, the change is happening at half, the change is happening at 0, and the change is happening at the last endpoint 1. So the first endpoint, the last endpoint, and wherever there is a break, we need to check the definition of the function for continuity by testing the ab initio definition. By ab initio, we mean that we need to check the left hand limit and the right hand limit and also the value of the function separately for testing continuity at different points. So let's begin our discussion by addressing 0. Now mind it, whenever the domain is a closed interval, let's say AB, here it's 0, 1, then there is no definition of the function on the left side of 0. So it will not make sense to talk about left hand limit of f at 0 because there is no f existing there. Similarly, on the right of 1, there is no definition of the function, so we will not be considering the right hand limit of f at 1. So to test continuity at 0 and continuity at 1, only one-sided limits will be considered. For all in-between points, here there are two in-between breakpoints, half and 3/4, we will be considering both-sided limits for testing continuity. So let's begin by testing continuity at 0. At 0, we can see f of 0 is given separately as 0, so f of 0 is 0, and for testing continuity, we'll just consider the right hand limit because on the left there is no f existing. The function has 0, 1 as the domain. For testing continuity, therefore at 0, we'll just bother about the limit of f at 0 plus the right hand limit. And right hand limit obviously will come from this branch because x more than 0 belongs to this segment of the domain. So we consider this definition as the definition of f when we are on the right of 0, and that gives us half minus 0, because when x tends to 0 it becomes half minus 0, that's half. Since these two are not equal, the limit is not the same as f of 0, and here the limit will be the one-sided limit only. We will not be bothering about the left hand side as I have told you just now. So since these two answers are not the same, so this is a discontinuity of what type? It's a removable one, because the limit is existing, the answer to the limit is half, and the value of the function f of 0 is not the same as limit, so the function is discontinuous and the discontinuity is a removable one. Let's move on to the next breakpoint, which is half in the definition. So let's look at half now. Now in this segment x less than half, what is happening? The value of the function is half minus x, and in this segment x more than half, the value of the function is 4x square minus 1. So the right hand limit of f will be considered using this value of f, and the left hand limit will be considered using this value of f, and f of half is given here separately as 0. So let's calculate them separately. F of half is 0, and the left hand side, the answer to f is this, so its answer will be half minus half 0. Similarly, when we consider the right hand limit of f at half, then it boils down to again 1 minus 1, that's 0. So luckily all three answers are the same, therefore the limit is existing and the limit is equal to the value of the function, so you have continuity at x equal to half, though there was a break in the definition at half, but half happens to be a point of continuity, not a point of discontinuity. Now moving on to the next breakpoint, which is 3/4 here. So let's look at 3/4. Now at 3/4, the value of the function will come from this branch only, because we can see that equal to 3/4 is included in this branch. So you'll get f of 3/4 and the right hand limit of 3/4 from this branch of the function, whereas the left hand limit will come from this branch. So when we talk about the left hand limit, the value of f will be taken as 4x square minus 1, whereas for the right hand limit we'll be considering 1 minus x square, and putting x equal to 3 by 4, we see that the answers are not matching. The value of the function is 7 by 16, the right hand limit is also 7 by 16, but the left hand limit is not the same as right hand limit, therefore it's a point of discontinuity of the first kind. Now moving on to the last point of discussion, which happens to be the right hand endpoint of the domain. It's 1. So let's test continuity at 1. Now obviously at 1 you'll be testing continuity only from the left. On the right of 1, the definition of f is not there, so we don't have to bother about the right hand limit. We just have to bother about the left hand limit and the value of the function. But surprisingly, x equal to 1 and x less than 1 are both covered in one go here in the last segment only, so there's no change for f of 1 and the left hand limit of f at 1, so both of them happen to be equal to 0, and hence f is continuous at x equal to 1. So this is how we test continuity of branched functions. We just have to bother about the break points in the definition of the function and examine the left hand limit, the right hand limit, and the value of the function at all the break points separately to conclude whether they are points of continuity or points of discontinuity. So that was all about the first question. Let's move on to the second question now. The second kind is, suppose there is a function which is defined as e to power 1 by x minus e to power minus 1 by x upon e to power 1 by x plus e to power minus 1 by x for non-zero values of x, and at 0 it's given separately as 1. So this function is defined basically on the whole of R, that's the domain. The question is to test continuity at 0, because you can see that this function is having a break in the definition at 0 only. Also, you have a continuous function above and a continuous function below, so you know that rational functions are continuous everywhere except at the points where the denominator vanishes. And this vanishes, the denominator is going to vanish if this happens, right? So in a way, e to power 2x, 2 by x should be equal to minus 1. So that means 2 by x should be equal to, exponential we know is never negative. So since e to power 2 by x is negative, so 2 by x is not a real number, it's not well defined. So that means such points do not arise where the denominator is vanishing. So it's a well defined function. There's a function which is a continuous function above, a continuous function below, and the denominator function is not vanishing at any real point. So this is very much continuous except at the break point. The break point happens to be 0, so you'll have to be carefully examining the continuity at 0. Now we see that f of 0 is given to be 1, so let's examine the left hand limit and the right hand limit at 0. So for left hand limit and right hand limit, the definition of the function is the same, but the behavior changes, as is clear from here. When you consider limit extending to 0 plus of fx, what is happening? When x tends to 0 plus, this is going to tend to infinity. E to power infinity we know is infinity, and this is going to tend to minus infinity, and e to power minus infinity is like 1 upon e to power infinity. So it's like 1 upon infinity, so that's a 0. So it's like infinity. So overall the answer here is infinity minus 0, and similarly here it's infinity plus 0. So basically it's infinity by infinity form. And whenever you have infinity by infinity form, either you can apply L'Hopital rule to get rid of this indeterminate form, or you can take out e to power 1 by x common to get rid of the infinity problem the way it has been done here. So when you take e to power 1 by x out, it becomes 1 minus e to power minus 2 by x, and similarly in the denominator also e to power 1 by x is common. So this infinity problem which was arising, we have cancelled it out by taking e to power 1 by x common from above and below, and what we are left with is, now since x is tending to 0 plus, so x is positive. So when x is positive, I told you whenever you see 0 in the denominator, be careful, you'll have to check the sign of the expression before you put a infinity or a minus infinity to it. Now this time, since x is tending to 0 plus, so minus 2 by x is negative and x is tending to 0, so it's like e to power minus infinity, and e to power minus infinity is 0. So 1 minus 0 upon 1 plus 0 is what it becomes, and that's equal to 1. Now moving on, when we consider limit extending to 0 minus of fx, now again the same expression is there, but this time since x is negative because it's lying on the left of 0, So it's negative because you are considering the left hand limit at 0. So you are approaching 0 from the left side of 0. So that means you are taking values of x which are negative. So it's basically 0 in the denominator, but the expression is negative. So it's going to be like e to power minus infinity. So this will be 0 minus infinity and 0 plus infinity this time. So the infinity problem, because when x is negative, so minus 1 by x will be positive, and positive expression with 0 in the denominator means infinity. So it's e to power infinity here this time, not here in the first term but in the second term. So when you do that, you have 0 minus infinity and 0 plus infinity arising out here. So that means the problem infinity is in the second term this time when your x is negative. So you take e to power minus 1 by x common now to cancel it out, and the remaining terms are e to power 2 by x minus 1 in the numerator, and e to power, this will be 2 by x plus 1 in the denominator. Now your x is negative and you have 2 by x here. So it's a negative expression with 0 in the denominator. So it becomes 0 minus 1 upon 0 plus 1. So that's equal to minus 1. Therefore, the two limits are not the same. One of them is turning out to be 1, the other one is turning out to be minus 1. And when we have such a situation where the left hand limit and right hand limit are two finite numbers but they are unequal, then we say that the point under consideration is a discontinuity point of the first kind. So this question tells you a lot of concepts which are involved, and the main concept which we had discussed in the previous video also is that whenever you do a upon 0, a is a real number, suppose a belongs to R, right, and you are doing a upon 0, then do not write a plus infinity straight off. It may be infinity, it may be minus infinity depending on the sign of a, and that is what becomes important here also, because when x is going to 0 plus, that means x is positive. So 1 by x is a positive expression with 0 in the denominator, so it led to infinity in the first term of the numerator. But when you do the other way around, when you take x tending to 0 minus, then 1 by x is negative with the 0 in the denominator. So basically this is e to power minus infinity this time, which is 0. And it's e to power infinity here, which is infinity. So infinity happens to come in the second term of the numerator when you're talking about the left hand limit. And that is what makes the difference here in the left and right answers, and that's why 0 happens to be a point of discontinuity of the first kind. So that's the second question. The third question, which is again important, is to, sometimes a function is given and you are supposed to put restrictions of continuity on the function to determine some unknown constant. So such questions are very common in the examinations also. So look at this function, it's defined in branches again. When your x is less than equal to 2, it's 1, and between 2 and 3, not including 2, 2 is included above. So open 2, close 3, it's ax plus b, where a and b are some unknown constants which we need to find out after assuming this function to be continuous. Now on the last branch, x more than 3, the answer is 8. The value of the function is 8. Now you can see that there's a break in the definition at 2 and there's a break in the definition at 3. Since we are imposing the condition of continuity, so if this function is continuous, it has to be continuous at the breakpoints as well. So if we exploit this condition of continuity at x equal to 2, what will we have? Left hand limit at 2 equal to right hand limit at 2 is equal to f of 2. But what is left hand limit at 2? We can see it's 1 from here, and the right hand limit of 2 will be obtained from this branch of the function, because this is where x more than 2 is covered. So when you put x as 2, you get 2a plus b. So this is the first constraint when you exploit the condition of continuity at x equal to 2. This is the first constraint on a and b that you get. Similarly, when you exploit the constraint of continuity at 3, you will get one more constraint. Continuity at 3 is again a 3-step process. Left, right and value of the function should be the same at 3. But what is left at 3? Left at 3 will come from here and right at 3 will come from here. So 8 is equal to 3a plus b. So that's what you get as the second condition on a and b. So these two constraints, so there are two unknowns a and b in two equations to solve for them. So two equations, two unknowns, we can easily solve for a and b to get a as 7 and b as minus 13. So such questions are very easy to handle, because imposing continuity condition on a function means continuous everywhere. So including the breakpoints, it's continuous. And we know that when such functions come, they are generally continuous at every other point. We just have to examine the continuity at the breakpoint. So you'll exploit the condition of continuity at the breakpoints and impose conditions on A and B and then solve for A and B. So let's move on to the next question. This is based on greatest integer function. We all know what is greatest integer function. It's defined as a function which is defined for all real numbers. It's the greatest integer less than or equal to that number. So suppose your number is between 0 and 1. So the biggest integer which is less than or equal to any point lying in this domain is going to be 0. Similarly, the definition will be 1 if you are in this segment. And similarly, if you are here, it will be -1. So this continues on the negative side also and on the positive side also. So that's how bracket x is defined. Now look at this function. This function is bracket x plus half, and we are expected to show that this function is discontinuous at every integer point. Every point which is an integer, and continuous at all it is discontinuous at all integer points and continuous at all non-integer points. I should be writing here non-integral points. So I missed out writing non-integral here. So this function is discontinuous at all integer points, because you can see that it's again a branched function with breaks happening at integers. There's a break at 0, there's a break at 1, similarly there's a break at 2, because for the next branch the value will be like this. So there's a break at 2, there's a break at 3, and similarly you have breaks at negative integers happening. So greatest integer function by definition has breaks at the integer points, and when we test for continuity, since the definition on the left or right of any integer is different, so that leads to discontinuity of this function at the integer points. But rest of it, suppose there's a non-integer point, the definition is going to remain the same, and hence you'll have continuity. So let's open this function. This function is an amalgamation of bracket x, x and half. You have to take the sum of them. So bracket x by definition is this. So you will have to define f of x also in branches. So we can see that f of x, when we are in this segment -2 to 1, then the bracket x value will be -2. So it's -2 plus x plus half when this segment is considered. Similarly, moving on to the next segment, -1 half, this is what it becomes. 0, 1. I'm just substituting the value of bracket x here. This is what bracket x becomes when you are between 0 and 1. 1 and 2, it becomes 1. And this keeps on continuing for all integers on the left side also, negative integers also, and right integers also. Simplifying this a little bit, because this is -2, this is half. So you can combine these two constants and further write your definition after simplification like this. So basically the question given in this, the function given in this question simplifies to a branched function which looks like this, and you can see that there's a break happening at every integer point. There's a break at -1, there's a break at 0, there's a break at 1, there will be a break at 2, 3, 4, and similarly -2, -3, -4, and so on. So there are infinite number of points where we need to test continuity. At all other points of R, there is continuity. At all integers we need to examine. So let's pick one integer and examine, because others will be very similar. So for every non-integer point, we see that the definition is the same in the, it's just a linear polynomial. So being a linear polynomial, it's continuous, so function is continuous at every non-integer point. But at integers, there's a break happening in the definition. So let's consider the first, let's take that integer to be -1. Let's take a sample integer. -1 on the left side of -1, what will happen on the left side of -1? This is the definition of f, because -1 left side is in this domain. -1 right side comes from here. So left hand limit at -1 will come from this branch, and right hand limit from this branch. And obviously, since the values are different in these two branches, when you put x as -1, you will get two different numbers as the answers to the limits. Left hand limit, the value of the function is x minus 3 by 2. So when you put -half, you get -1, you get -5 by 2 as the left hand limit at -1. And similarly, when you put the value of the function as x minus half for the right side of -1, you get -3 by 2 as the limit for the right side of -1. Since these two answers are not the same, f is discontinuous at -1. So this was one sample integer which we had picked. Similarly, we can show that f is discontinuous at every integer point, and we can note since left and right are existing but they are different answers, such discontinuities are called discontinuities of first kind. So that means all these discontinuities, all the integer points happen to be discontinuities of the first kind for this particular function. So you can have any kind of amalgamation of bracket x done here. The only thing that one should know is, since bracket x is defined in branches, so if there's a function which is involving bracket x, it automatically becomes a branched function, because bracket x is a branched function which has infinite number of branches. So any function which comes in the question involving bracket x is going to naturally become a branched function involving infinite number of branches, and such functions will surely be discontinuous at every integer point, because there's a break in the definition of the function at every integer point. So that's how we address such problems. Now look at this sample problem. We have to examine the continuity. Again, there's a function which is branched. There's a break happening at 2. F of 2 has been defined separately as 0, whereas left and right answers are given by e to power minus 1 by x minus 2 square. Now the important point here, because of which this has been included in this miscellaneous set, is going to be conveyed in a little while to you. Let's consider the left and right hand limit of f of x. Now I told you, whenever you see 0 in the denominator, please do not put a blind infinity. You have to be careful, because in this question we saw, in one of the questions above, we had seen, from here when x was 0 plus 1 by x was infinity, but when x was 0 minus 1 by x was minus infinity, so e to power minus infinity was 0. So that made a difference to the calculation. Now here what happens is, sometimes whether you are on the left or right, irrespective of that, the expression is such that it does not matter and gives you the same sided infinity. For example, in this question, if you consider the left hand limit at 2, it becomes limit extending to 2 minus of this. Now what will happen when x is less than 2? X minus 2 is negative, but luckily it's a square here. So whether x minus 2 is positive or negative, it's not going to matter, because you're going to square it in the end to make it positive. So minus 1 upon x minus 2 square therefore will be negative, irrespective of whether you are on the left of 2 or right of 2. This sign is going to be always negative, and you are putting 2 in the denominator, so it's actually minus 1 upon 0 happening. With a negative expression with 0 in the denominator is always minus infinity. So it's like e to the power minus infinity, and we know e to power minus infinity is 0, because e to power minus infinity is 1 upon e to power infinity. Now surprisingly, when you move to the right of 2, it does not really make any difference to this expression because of the square thing here. X more than 2, x minus 2 positive, x minus 2 positive, or x minus 2 negative, this overall expression will be negative. So when you have a negative expression with a 0 in the denominator, it's again e to power minus infinity, leading to the same answer, which is 0. And luckily in the definition of the function, f of 2 was defined as 0 separately, so all three happen to be the same. F of 0 is equal to 0, left hand limit at 2 is 0, right hand limit at 2 is 0, all three are equal, so f is a continuous function at x equals 2. So this question becomes typically important in the sense that 2 minus and 2 plus do not make any difference, irrespective of the fact that we need to check the sign. But since there was a square involved, so sign was not mattering here, because when you square, even the negative becomes positive. Now there are some questions for practice which you can take screenshots and solve here. Test for continuity, the function 3 mod x. Mod x, I hope everyone knows here. Mod x is modulus function or absolute function, absolute value function. It takes the value, the same x. If x is greater than 0, the value will be x only. So let me write it properly for your help. So bracket x will be the same as x if your x is non-negative, and it will be minus x if x is negative. So accordingly, you will be breaking this function into 2 branches. These x not equal to 0 will be broken up into 2 branches. For x equal to 0, the answer has been given separately as 3. So this is one practice problem which you must try. The second problem, again a branched function. The break is happening at 4, so you'll have to test continuity at 4. Another problem, mod x upon x. Again, you'll exploit this, that mod x is a branched function branching at 0, so you will be branching this also accordingly. Fourth question, you have x non-zero, this is the value of the function, and x equal to 0, this is the value of the function. So you will find out the limit, and limit will be obtained using L'Hopital rule, and you will have to see that 0 minus and 0 plus is the same as f of 0. So this is again worth trying. Again, there's one problem which is a branched function, so you will test continuity at 0, you will test continuity at 1, you will test continuity at 2. For rest of the points, there's no problem because they are all continuous individually in branches, so you just need to check continuity at the breakpoints. Now the next question, you need to find out the value of k so that the given function is continuous. As I told you in one sample problem above, whenever you impose continuity condition, it's continuous everywhere, and since there's a break here at 0, so you will find out the limit at 0 from the left and right and equate it to f of 0 to obtain the value of k. So that is all about questions, various types of questions which can be made on continuity. So these are sample problems through which infinite number of problems can be generated, and in this practice set which I have just now highlighted, if there are doubts, you can please post them in the comment section or mail to our email ID which is mentioned here. We'll surely get back to you and try to clear your doubts. That's all for this video. Thank you so much for watching.